Welcome to TMC 2021 Online. This session, like many others, has been pre-recorded and is available on demand. Road-friendly suspensions and shock absorbers. These are two subjects that always ensures engagement from operators. Everyone, it seems, has an opinion. For this session, we have two leaders in each of their fields. Our first speaker is Luke Callaway from Hendrickson. Luke is the Executive Manager, Engineering at Hendrickson, Asia Pacific, and has been involved in RF road-friendly suspensions for most of his professional career. Our second speaker is Adriaan, who is the Engineering Manager at Powerdown, Australia. He's a self-professed petrol head and has been involved in automotive design, manufacturing, and vehicle dynamics. So let's get started, and over to you, Luke.
Thanks, Bob. Thanks very much for that introduction. And thanks for having me at TMC Online. It's always great to be involved in events like this. And I know I've been involved with TMC before, and it really is a great event, and very happy and privileged to be able to be a part of it again in this online format. You heard who I am, and what I'm going to talk about along with Adriaan is road-friendly suspensions. What I'll cover is a bit more of an overview on, I guess, the basics and the process and the suspension side of things, and then I think Adriaan's going to dive into a bit more detail on shock absorbers and their role. So I'll talk about what is a road-friendly suspension, why do we have them, a bit of background on road-friendly suspensions. Some of the administration and compliance, which I guess can be a bit dry, but it's important to understand just the basics there, and then some of the implications on design and maintenance of road-friendly suspensions. So what is a road-friendly suspension? Well, it's a suspension that meets a set of performance criteria, basically, under a particular test condition. So there's a test that's conducted in order to certify a road-friendly suspension, and it involves an 80mm step. There are actually a few different test methods, which I'll cover a little bit later in a little bit more detail, but essentially there's a test where the suspension is dropped 80mm, and then some characteristics are measured. So one of the characteristics is that the suspension needs to have a frequency, or a free transient oscillation frequency, of 2 Hertz or less. So that's how quickly, I guess, the suspension bounces up and down, how many times per second. So it has to bounce up and down no more than 2 times in 1 second. The damping on that suspension needs to be above a certain level. So that's 20% of critical damping, which means, critical damping is where basically it drops and it doesn't bounce at all. It needs to be at least 20% of that level of damping, and the other one being that at least half of the damping needs to come from dampers, so components that are designed for damping the suspension. There are some other specific requirements to different regions where road-friendly is employed, and I'll go into that in a bit more detail in a second. Why have road-friendly suspensions? Why are they a thing? Well, I guess it's to protect the road, as the name implies, and that ties into, I'm not a pavement expert, but at a very high level, the basics of it are that, the damping requirements. So basically, what the damping does is, you'll hit a pothole, you'll get a bounce, and then it's how large are the bounces and how many bounces do you get subsequent to that initial input, say from a pothole. So reduce the size of the oscillation, so that's having a high enough level of damping. And then it's the distance between the oscillations. So I guess if you hit a pothole, then how many times, or what distance from that initial input is the next input, and therefore the next input after that. And I guess that ties into road damage. If you've got a lot of high impacts close together, that's more damaging than if you have a high impact and then there's quite a distance until the next bounce. So that's tying into your frequency component of the requirements that I mentioned on the previous slide. And then what all that does is basically reduce the cost to the asset owners or the road owners in maintaining those and coming and fixing potholes, etc. So obviously, if you own a road, that's a great thing, but you want to incentivise the people who own the vehicles that have the suspensions to comply with that in some way. So the way that they do that is to give operators more payload or higher axle loads on their vehicles. So higher mass limits is the main scheme, which is used as a mechanism for doing that. I'm sure a lot of people listening are familiar with that scheme, but there's a number of requirements to be running higher mass limits, those higher axle loads, one of which is that the suspension is road friendly. Mass management is required. In some states, Intelligent Access Program or IAP is required, where there's some tracking on vehicles, etc. And there is some limitations around the different roads that you can travel on. There are actually other schemes as well which don't require road friendly, which maybe is a little less known. So CML, concessional mass limits, is another tier within this system, and that doesn't actually require road friendly suspension. So it's only the top tier, which is high mass limits, that requires that. And there are a few other schemes that tie into road friendly, but the main one is HML. And as I mentioned, it all is based around improving productivity for the operator and end user, carrying more payload on the same truck. So I guess most people watching this presentation are probably interested in Australia, but just as some background, and it does tie into how it's been implemented in Australia, is it actually was first introduced in Europe around 1996 under a directive that's shown there, if you want to look it up. And the intention there in Europe, as I understand it, is to show equivalency to air suspension. So it's basically an air suspension is deemed to comply, so there is no testing and compliance of air suspensions in Europe for road friendly. And another alternative pathway to getting the extra mass on the axles is also to have a load sharing suspension. So it's the same but different, and there's probably a lot less prevalent use of road friendly in Europe as a result of those alternative pathways. Another small difference is hydraulic dampers are specifically called out in Europe, where I'll talk about Australia in a minute, but specifically hydraulic is mentioned there. And multiple test methods were defined in that. And so I'll go into a little bit more detail now on those test methods. So you saw on the first slide, there was an image of a step that was 80 millimeters high. And basically you can drive over that step with that profile at 5 kilometers an hour and measure the response is one method. Another method is you can lift the chassis by 80 millimeters and leave the axle on the ground and drop that chassis and measure the response there. And the third one that's specifically called out is pulling the chassis down to 1.5 times the static maximum axle load, letting it go, letting it oscillate and measuring that response. And then there's a fourth one, which is basically another method that is shown to be equivalent and approved as being equivalent to any of those methods mentioned. So that was all defined within the European framework, and it is it's called out in that document that's referenced up the top there. So moving on to Australia, which is probably what people are a bit more interested in. It was introduced not long after in 1999. And it's called it's outlined in Vehicle Standards Bulletin 11, or VSB 11 as people talk about it most commonly. And it's actually a national code of practice. A couple of differences to what is in Europe. The air suspensions are not deemed to comply, hence they need to be tested to meet those criteria. And I mentioned before, there's a hydraulic damper requirement in Europe. There's no specific requirement for hydraulic dampers in Australia. The load share is required within 5% between axles, which is an addition to the Australian requirements. But the test methods are actually just adopted straight out of the European requirements. So actually, as an annex or an appendix to the VSB 11 document, the European document is appended in there the specific parts that talk about the test method and a few other things. So that's purely taken straight from Europe. So they're exactly the same in terms of how you test. So how is it administered in Australia? So basically, in order to test a road-friendly suspension, you need to be a registered test facility. You can't just be anyone with the ability to do so. You've got to be registered. And then once the test is completed, it needs to be reported and submitted to the department, which tends to change names fairly frequently, but I think it's currently the Department of Infrastructure, Transport, Regional Development and Communications. They review the report, and then they will make a decision on whether that's approved or not based on the information in that report. And then they'll assign a unique ID, an RFCN, Road Friendly Certification Number, and a certificate gets posted online. Another requirement is that the number is actually displayed on the vehicle for it to be considered road friendly. I'll go into what's posted online on the next slide actually in a bit more detail. So, and this is where it ties into what you need to consider when if you're modifying or servicing a road friendly suspension. But just on the certificate itself, so when they do register that, there's an example over there on the right of a certificate. There's a table and it specifies parameters about that suspension. So there's that ID number for that suspension, and then there's a number of variants you can add to that certificate, and for each variant the specific parameters are called out. So the number of axles, the type of suspension, whether it's overslung or underslung, maximum axle spread within that suspension if it's more than one axle. The damper part number is specifically called out, the smallest size of the tyres, the highest tyre pressure you can run, the air spring or airbag diameter, and then a reference drawing which outlines the, I guess, the dimensions and the installation of that suspension. So that's important to know because it also ties into compliance. So basically those things that are in that table, I've got an excerpt here from VSB 11 on the left, and that highlights actually any of the things or characteristics of the suspension that if you were to change that, you would be required to register a new variant or a new certification for the suspension. And it basically ties into the rows in the table for the most part. So it's important to know that if you're working on a road-friendly suspension, that if you change any of those things, you might need to submit a new approval in order to stay compliant with road friendly and keep running your higher mass limits or under another scheme if you're doing that. So those things might include changing the geometry of the suspension. If you mount something in a different way, you change a shock bracket or change where the shock's mounted or some other geometry of the suspension. If you change the shock absorber, even if it's from the manufacturer, but it's a different part number, it actually has to be listed on the certificate, that part number. If you changed an air spring, all those sorts of things would mean that a new variant or the variant or that particular certificate would need to be updated, which is also possible. You can submit a variation on a variant if you've changed something and it still complies. So important to know that when you're working on road-friendly suspensions, that's the framework you're working within in order to stay compliant. So moving on from some of that more dry stuff to some of the stuff that I enjoy a bit more, which is suspension design. So I just thought I'd very briefly talk about some of the implications on designing suspensions in terms of road-friendly and meeting those requirements. So, I mean, I guess the main thing with road-friendly suspensions in terms of design that might be different to non-road-friendly designs, it may not be, but is, typically you might need to add some more damping in order to meet that damping requirement of 20% or greater. So if you add more damping and you leave the geometry the same, so say you imported a suspension from another market that had a lower level of damping than 20%, and you wanted to maintain where the shock absorber was mounted, say it was a suspension with a shock absorber that was providing the damping, then you would need to increase the force on that shock absorber, or at a particular velocity, or the performance curve on that shock absorber to get a higher damping level. Then something you need to consider is the strength of the mounting points. So that's a key consideration in that scenario. The suspension might be designed from scratch to already have that level of damping, and it may be okay. But if you were to, bring in a suspension with lower damping, you need to increase that, then the mounting points might need to be stronger. And a key consideration when looking at mounting point design is fatigue. It's something that we focus on a lot when designing suspensions. So what that means for anyone who's not familiar is basically, a part might be able to take a particular force or stress. So when you apply a force to a component, it creates a stress in that component. So it might be able to withstand that level of stress one time, but then if it's above a certain limit, above a certain level of stress, which is referred to as the fatigue limit, then there's a limited number of times that stress can be repeated on that component until eventually it will fail. So this graph over here on the right shows stress amplitude up on this axis, and the number of cycles or number of times that stress level is applied to that component before it breaks. So if you look at the blue curve, so if it's below what they call the fatigue limit, then it essentially lasts forever and you can apply that stress as many times as you like. But if that stress is above that limit, then there's a certain number of times you can apply that stress before it fails. So that's something, given a suspension goes up and down a lot of times in its life, and hence a shock absorber goes up and down a lot of times in its life, then you need to consider the full life of the component, not just whether driving out of the car park that's going to be okay, or for the first 10,000 kilometres, you need to consider the whole life of the suspension if you're going to elevate the stress and forces going through that suspension each time it goes up and down. And then for air suspensions, it's typically the damping that's a focus. So an air suspension would typically have a lower spring rate, and that's because it's a variable spring rate by nature. It's controlled based on ride height. And so as you increase the load, the pressure increases and therefore the spring rate increases. And so that allows you to have a lower spring rate because it adjusts to what's required to carry the load. And so generally your focus would be to make sure you're meeting that damping requirement. For a mechanical suspension, it's typically, a more fixed spring rate, and therefore the maximum capacity of that suspension would typically drive the spring rate, meaning it's typically a higher number. And therefore, to meet the road-friendly requirements, you might also need to focus on that frequency criteria as well as the damping, given you would typically have a higher spring rate for those types of suspensions. So there's some of the considerations around, depending on what type of suspension you're looking at in terms of ensuring it meets road-friendly requirements. And then finally, some main considerations to take away when installing or maintaining a road-friendly suspension. So has it been designed and validated for road-friendly levels of damping, which I spoke about in terms of fatigue, and if you're if you're taking a non-road-friendly suspension and you're turning it into a road-friendly suspension, have you considered all the the life of that suspension and whether it can withstand those loads? And then if you're maintaining it, does it still comply with the certificate? So have you changed the geometry, or have you changed the part from what was listed on and certified on the certificate if you're going to maintain and modify in any way? And then another point is, so suspensions often will have attachments that directly attach to a chassis or a cross member. rather than being self-contained within the suspension, depending on the suspension itself. And so it's also important to consider, you know, can the chassis, can the cross members, can the attachment points also take the level of force going through the suspension if it is a, you know, if it's transmitting a higher load through particularly the shock absorbers generally. And shock absorber mounts, is a doubler plate required behind the shock mounts, or is there some sort of extra reinforcement required? So yeah, they're probably the main things to consider. And yeah, so I hope that presentation has given you something new, something useful, something to consider. And I look forward to receiving some questions during the conference if anyone has any that they want to ask. So I might hand over to Adriaan to talk a bit more about shock absorbers and road-friendly suspensions.
Thank you, Luke. Hi everyone. As Bob said, I'm Adriaan. I'm engineering for Powerdown, Australia. I'm really excited sharing this session with Luke, and I'm looking forward to some interesting conversation around this fairly technical topic around road-friendly suspension. So I'm going to kick off just covering some suspension basics, some basic shock absorber design, and then I'm going to talk about the limitations in developing a shock absorber for RFS suspension with completing a fully assembled certification test. So just quickly on the suspension side of things. So you know, your suspension needs to keep your wheels on the road. So we maintain good friction that allows us to corner and brake. To a big extent, you know, the suspension also provides you know, some comfort to smooth out you know, some of these vibrations. And for today's topic, very importantly, is your suspension is a big part of making your vehicle compliant to VSP 11 or road friendly. So you know, basically the springs allow that the cushioning. You know, it carries the load and it absorbs that unevenness in the road. But a side effect of that is it turns these motions into vibration. So the shock absorber is then tuned to remove these vibrations, or you know, to dissipate that energy. And it's also important to note that, you know, the shock absorber does not contribute to that load carrying capability of the suspension. Just fundamentally, there's two types of shock absorber designs mainly used. They're mainly twin tube or monotube derivatives. We'll see on modern trucks, the new Tesla truck seems like some sort of monotube technology on those, but predominantly, especially in the Australian market, twin tube shock absorbers are the go-to technology. For twin tube shock absorbers, you've got two tubes. You've got an inner and an outer tube. You've got different configurations with or without gas. So as per this video, we can see this is a twin tube design. This is more like a strut type of style design, but you can see the inner tube. You've got lots of valving. We're going to talk about that later on the main piston, as well as a flooding piston. And then on the outside, we have this reservoir tube, which basically displaces the oil as the piston rod enters the body. For a monotube, we only have one cylinder of the gas and the oil, never mix. It's got better heat dissipation. It's got a bigger working piston for the same body size. So on the truck side, I think the common application for this is there's some Kenworth cab dampers, which is monotube technology. So you can see the main piston moving inside. You've got a oil and gas separator with a floating piston. And then all your valving is happening on the main piston. So no foot valve in this design. So just some characteristics of the shock absorber. So we've basically got the length, so the collapse length and the extended load called the stroke, mounting points. Very important, like Luke mentioned in his presentation, how this damper basically mounts to the vehicle and to the axles. Your mounting bushes, you know, your selection of those materials and design also plays a big role in how vibration is translated into the rest of the structure. You know, you've got the outside or cylinders. So you've got steel dust covers or plastic dust covers. That makes up how the shock absorber basically looks from the outside. So just basic measurements, so extended lengths, so the different ways we measure it for different shock absorbers and different mounting configurations. So pin, II, or pin-I combinations. Internally, if we look at the shock absorber, as we said, a twin tube, we've got this foot valve, which plays a big role in your compression valving, and then you've got the valving on the piston. So we've got lots of different designs how to deal with the recoil damping, and then obviously some compression dampening happening on the main piston as well. So how dampers are tested is basically we cycle them through a sinus displacement graph programmed at a set frequency, and then we can basically record the forces generated. So according to international design standards, this is a typical force displacement graph. So each of these lines above zero basically represents a recoil damping force at a velocity. Under the zero mark, so the negative forces are seen as compression forces generated by the damper at specific velocities. So these velocities are really important when we design the damper for road-friendly suspension. So we'll get to that. The typical shock absorber today has got fairly intelligent valving, if we can call it that. It's speed sensing, so it's non-linear is what I want to highlight. So the damper reacts differently at different velocities. So if we talk about the non-linear characteristics for a shock absorber, meaning you're not going to have a set output of force relative to the velocity, so it can adjust itself through a wide spectrum of velocities. So a typical self-adjusting or speed sensing damper will have a basic and orifice stage, which is all these stages are fairly important when designing a damper for road-friendly suspension, but at the lower speeds and the lower velocities, those forces we generate, we call the orifice stage. Then there's a blow-off stage at the medium velocities, and then we go into a restricted stage at higher velocity. So that's the amount of oil we can displace through a certain design. Okay, and this is true for basically the compression and the recoil cycle of a damper. So if we combine, if we combine all those three stages, so we can see the orifice stage, and then as we go into saturation and blow off, combining all three of those, we basically get our recoil and compression damping curves. Okay, so it's got this compounding effect. So Lucas covered this in detail. I would just like to highlight what he said and how the damper affects it. So the suspension needs to oscillate below that 2 hertz. I just want to mention that if we overdamp the system, we can actually increase that failure. So we can have a compliant suspension spring or spring rate, which is compliant, but if we overdamp the system, we're going to actually start increasing that frequency. Okay, then we're going to talk about, as Luke touched on, the mean damping rate and the different damping ratios. And then, the static load sharing, that falls outside what the damper brings to the shock or to the suspension design. So on this video here, I've got these little videos. So as Luke also touched on, if we overdamp the system, you can basically say it takes very long to return to the static position. If a system is critically damped, it will return to the static position in the shortest possible time. And if we underdamp the system, then we can see this oscillation happening with just like a decrease in amplitude of that motion. Okay, so let's talk about the drop test. So just one of the common methods, so dropping from 80 millimeters height. So we've got a starting point marked. So from a damper perspective, what happens is we're going to drop the suspension, and it's going to reach a point A where it turns around and where it's going to start returning or moving upwards. Okay, so there's a bit of maths involved on the damper, looking at what actual damper velocity is achieved through these different phases of motion in the drop test. So keeping in mind to have a good damping rate, there's a formula we apply between the amplitudes of point A and point 3. And the damper needs to absorb the right amount of energy to have a pass damping rate. So from the drop test, we start at 80 mil, we drop down, which means the damper goes into compression. And that's the quickest damper velocity which is going to be achieved during this test. So normally we find, for a damper with a motion ratio very close to 1 to the axle velocity, but we have a peak, compression velocity, just under that 0.52 meter per second velocity. Then the damper is going to turn around, so it's going to basically start extending or going into its recoil cycle back up to a peak, which is called A2. So to start generating a fairly large gap between these two amplitudes, obviously we want to ensure we absorb sufficient energy in this phase. So for a damper with a motion ratio close to 1, you'll typically find that that velocity is just under 0.39. So in that restricted phase, as we spoke about in the damper design. And then we're going to start dropping down again, going back to point A3. So then the damper is going to enter a compression cycle again at much lower velocity, just around 0.13 meters per second. So these are fairly important fundamental things to understand when you design this damper for a specific suspension. And as Luke said in his presentation, the suspension wants to oscillate at that natural frequency, which must be under 2 hertz. So we have to reduce these amplitudes. So and that's the damper's energy is dissipating to achieve that result. So from a design perspective, for example, we know we want that difference between A1 and A3 from a damper design. We can basically tweak the compression values at A1 to make it more compliant. So we have a much larger drop. And then, you can stiffen A2 or the forces generated here in the recoil cycle to reduce the peak at A2, so to absorb as much energy as we can. And then point A3, so at the lower speed, you can tune that again in that range to have adequate difference there to be able to get that correct damping rate. So that's in principle, in basic terms, how we adjust the damper and the damping forces relative to a drop or to a suspension and basically the VSP 11 test method. Thank you. I'm looking forward to some questions as well.
Thanks, gentlemen. Well, Adriaan, I'd have to say that was a shocker presentation in a good way.
In a good way?
In a good way. Look, thanks to Luke and Adriaan for taking the time out of your day for those very technical presentations and your participation in TMC 2021. Luke and Adriaan are part of the ITC gang, and to those delegates, by becoming an ITC member, you'll get the opportunity to meet and converse with members such as Luke and Adriaan, who have lots of technical and practical resources. To the delegates, please direct your comments and questions via the comment box. And finally, I must say again, very informative presentations, but I'll leave delegates with a question. Do we need a standard for suspension and shock absorber friendly roads? Thank you all.